Here are solutions to homework set number 10 for ECE 461 control systems. In this homework set, we're looking at z-transforms, converting from the s-plane to the z-plane, and root locus in the z-plane. Now, the first problem is, given a transfer function in z, what does it mean? Well, s means the differential equation, z means a difference equation. So once again, multiply out the polynomial, cross-multiply, and in the z-plane, z means next value. So this is y, 3 samples in the future, y, 2 samples in the future, 1 sample in the future, the current value of y, x, 2 samples in the future, and current value. So here is the difference equation that corresponds to that transfer function. And some people don't like using future values, so I can just do a change in variable and shift everything by 3. That's also perfectly valid. Either one's a valid difference equation representing that transfer function. Problem 2. Suppose I have a system where x and y are related by this difference equation, and x is a sine wave with a known sampling rate. What is y of t? Well, this is actually a phasor problem. Since this is true for all time, I know that the answer is going to also be a sine wave at 4 radians per second. What I don't know are the cosine and sine terms. I don't know these two weightings. To find them, use phasors. So in phasors, I represent x as 2 minus j3, the real part's cosine, minus j is sine. S is j4, that's the frequency of oscillation, and z is e to the st. So if you're using MATLAB or an HP calculator, you got no problems. If you're using a TI calculator, TIs don't really like complex exponentials. In radians mode it works, otherwise it doesn't. But anyway, using a calculator that does work with complex exponentials, this is the gain at all frequencies. All I care about is what's the gain at z is e to the j 0.04. Times the input at that frequency gives you the output. Now, just like in the s-plane, that's a representation of a sine wave. The real part is cosine, minus j is sine. So here's the answer. So again, analyzing filters in the z-plane is just like the s-plane. The only difference is I have to know the sampling rate, and z is e to the st. Otherwise, it's just a complex number. Problem number 3. Suppose instead x is a unit step. Now find y. Now this is where you need to use z-transforms. I take the z-transform of a unit step, that's z over z minus 1, times my gain, that's the z-transform of y. Now this is not in my table of z-transforms, so what I'm going to do is pull out a z, do a partial fraction expansion, multiply through by z, and now I can take the inverse z-transform. So this is 0 plus 1.125 times 0.9 to the k, minus 1.33 times 0.8 to the k, plus 0.2083 times 0.5 to the k for k positive. Problem number 4. Suppose I have a filter in the s-plane. What is the discrete time equivalent? Well, there's a couple ways of doing it. The approach I like using is say that z is equal to e to the st. So if I know s, I know I've got 3 different poles in the s-plane, I've got 3 poles in the z-plane. The conversion is e to the st, so take minus 2.6338 times t, e to the x, I get a number. That's the first pole. Repeat at the second pole, repeat at the third pole. So this is the form of g of z. The gain's wrong. To get the gain right, match the DC gain. So take g of s at DC, the DC gain is 0.5070. Pick k so that g of z also has the same gain at DC. At DC, s equals 0. At DC, z equals 1. So doing that, here's k, and here's your k of z. For this class, that's good enough. Optionally, what you could do is add a couple z's in the numerator. If I plot the step response of this system, it has too much delay. Every time I multiply by z, I move forward in time by 1 sample, 0.1 second. It's add enough z's until the 2 step responses match up. You get the right amount of delay. I can do that by trial and error. That's perfectly fine. Another way is you can actually calculate it. Pick a frequency, I just chose 1 radian per second. Here is the phase of g of s, minus 23 degrees. This is the phase of g of z, minus 35 degrees. So there's too much delay in g of z. Every time I multiply by z, I add 5 degrees phase shift. So how many z's do I have to add so that minus 35 becomes minus 23? So n is 2.07. I need to add 2.07 zeros. I can't do fractions, so let's round to 2. So this is a slightly better version of g of z. This has the same DC gain, corresponding poles, and almost the right amount of delay. It's a little bit wrong because I need 2.07. I can't do fractions. No points off if you don't put that term in there, but it's a better model if you do. And better models give you better responses or better results when you design your feedback controllers. If I plot the two step responses, I can do that as follows. I'll do step of GZ, that gives me the blue stair-step line. I'll hold that graph and then plot the step response of G of S, that's the red line. And you can see the two responses are almost identical. That's a pretty good model for the system. Problem 5. Suppose somebody comes along and says, you know, I'd like the sampling rate to be 0.01 second. Now give me the discrete time equivalent. Well, in controls, that's a big deal. If you change the sampling rate, I change everything. So it's basically a complete redesign. So changing the sampling rate is a big deal. To illustrate that, take the previous design, scrap it, start over. I've got 3 poles in the S-plane, a new sampling rate. Now where the poles are, is z to the st. It becomes 0.97, 0.73, 0.58. Completely different location. Repeating, here's the form of g of z. To match the DC gain, I need to multiply by 0.0014. And that's actually fairly common in the z-plane. This is a very small number. That just says in one sample, in 10 milliseconds, the output doesn't change very much. To get the right number of zeros, I can do the same trick. Pick a frequency, like 1 radian per second. What's the difference in phase shift between g of s and g of z at that frequency, divided by how much phase each z adds? I need 1.7 zeros at the origin. Again, I can't do fractions, so let's round up, call it 2. So here's my discrete time version of g of z when the sampling rate is 0.01. And notice completely different design. Change the sampling rate, everything changes. Again, if I check the step response, the two match up pretty darn well. Again, a little bit to the left. That's because they need 1.7 zeros. I rounded up to 2, so there's not enough delay. Problem number 6. Given the last problem, when the sampling rate is 0.01, find the feedback gain k that gives you no overshoot for a step response. So the first step is draw the root locus plot. So I've got 2 zeros at the origin, 3 poles, draw the root locus. Here's what she looks like. So here's the unit circle, there's my poles. Root locus is just roots to polynomial. The root locus, the mathematics behind it, doesn't care. Are you S-plane, Z-plane, W-plane, whatever. It's just roots to polynomial. So that's what the root locus looks like. Now, given the root locus, I can design for different responses. Suppose I want no overshoot for the step response. That means design for this point, the breakaway point. So on any point in the root locus, once you find your point, at any point, the gain, g times k, is minus 1. Here's g of z at that point. The gain is negative, which is on the root locus. Gain is wrong. Pick k to make the gain 1. K is 0.04. If I then take the step response of the closed loop system with that value of k, I get just what I expect. No overshoot. Real pole. There is a settling time. The settling time is the log of 0.02 over log of z. What is z? 0.86. That's in k times the sampling rate, 0.01. That's your settling time in seconds. So it's behaving like I expect. Problem 8. Suppose I want 20% overshoot instead. Well, the blue line is my root locus plot. I need to draw the damping line. In the z-plane, this is the log spiral, so I can't just take a line and draw an angle. I've got to get this damping line in there, and that isn't shown in MATLAB. To get it, what I can do is draw the root locus plot. I need to say hold on. Freeze that plot, and then do the red line, the damping line. To get 20% overshoot, I want a 2-to-1 ratio. That gives you 20% overshoot. I'm going to guess the root locus crosses the S-plane, the root locus in the S-plane, somewhere between the real part of 0 to 100. I don't know where it is, but let's just say it's in that range somewhere. Convert S to the Z-plane. Now on top of the root locus plot, plot the real part of Z and the complex part of Z. That gives you the damping line. That's 20% overshoot. Where the damping line intersects the root locus plot is your solution. So in this case, zooming in, that's 0.86 plus j.19. At any point on the root locus, g times k is minus 1. Pick k to make the gain 1, k is 15.5. So if I plot the closed loop response, there's your 20% overshoot. Or in VisSim, VisSim's a little bit better. This is your g of s. I was kind of struggling with that, so I split up into 3 parts. G of s, input it however you like. There's my gain k. This is actually a transfer function with a sampling rate of 0.01. 1/1, so it's just a sample. Gain of 15.5. So here's the input u, the blue line. You can see the discrete time sampling. And the red line, 20% overshoot. Finally, for a damping of 0, I want to find out where does it cross the unit circle. So here's the unit circle. I want to find this point. Zooming in on it, that's 0.85 plus j.51. Pick k to make the gain 1 at that point. K is 113. Plot the closed loop response. And there she is. Or in VisSim, I apply again 113. Here's my g of s. This is actually unstable, so the gain's a little bit too high. The reason it's too high is my discrete time version of g of z underestimated the delay. The extra delay destabilizes it, making the g omega crossing go unstable, right half plane. So that's one way to do the homework. As a sidelight, this is optional, but this is the way I like doing it. With root locus, you don't really need the root locus plot. All I need is a single point. So what I'm trying to do is, in the S-plane, I want to know where on the S-plane is the phase 180 degrees. That point is your point on the root locus plot. I don't need the root locus plot. All I need is that one point. So I'm going to search where on the S-plane the angles add up to 180. And instead of converting to the Z-plane, I'll leave this alone. That's g of s. There's no approximations then. This is my sample and hold. Sample and hold looks like a half sample delay. And there's my k of z, just to gain k. Where in the S-plane do the angles add up to 180? And using numerical techniques, just keep on iterating until I find where the angles add up to 180. I find the solution is actually at J36 in the Z-plane. Again, Z is e to the st. That's where it is in the Z-plane. That's actually where the root locus crosses the unit circle in the Z-plane. At that point, angle's 180, gain's wrong, pick k to make the gain 1. K should really be 47, not 115. And if you try it in VisSim or Simulink, here's my continuous time system, there's my discrete time controller. I can see the discrete time controller, my stir steps, and the oscillation is actually decaying slightly. This is slightly left half plane, slightly stable, but pretty close to the j omega axis. Now in terms of which method is best, using the root locus, this approach, or using this approach, I would argue the one that gives you the right answer is the best way to do it. I personally like this approach. It's, in my mind, easier. I just have to do a numerical search for g of s times delay times k of z, and I get the point. So it's sort of root locus, sort of not, but it gives you the right answer. On the homework, use whichever method you like. So that is homework set number 10 for ECE 476.